In this video, we're going to go over what differential equations are, the different types of differential equations that you'll deal with in a Calc AB and BC class, and how you can solve one. So let's jump in. To start, let's ask the most basic question, what is a differential equation? Go ahead and pause the video and see if you can answer that. Basically, the way that I think about a differential equation is a derivative equation. So when I think of differential, the word differential basically just means the adjective of derivative. So you can think of differential equations as derivative equations, or in other words, any equation that has a derivative in it is technically a differential equation. Now let's start off with one of the simplest differential equations that you'll see in a Calc AB or BC class. This thing clearly has a derivative in it, so it counts as a differential equation. The next question is, if it's an equation, how do we solve that equation? It's a little bit different than the algebraic equations that you're used to in the previous years. In those equations, basically what you're trying to do is to find the number or numbers, there could be multiple answers, that make the equation true. So for example, in this equation, I won't go through how to actually solve it, but I'll just leave it to you to verify that x equals 2 and negative 2 both make this equation a true statement. And then what does that really mean? Why are those the solutions? Basically, if you take this value of x and you plug it in to the original equation, you will get a true statement. So if I plug in 2 or negative 2 for x right here, I'll get 4 minus 4 equals 0 or 0 equals 0, which is a true statement. If I plug in any other numbers, I will get a false statement. So if I plug in 0 or 1 or whatever, anything like that, I will get a statement that is not true. That's how you can tell if your solution to the equation is correct or not. Basically, if you plug your solution in and you get a true statement, then it's true. If you plug it in and you get a false statement, then it's false. So in this case, the real question is, what value of y, and just to point out, y is not a number like x is over here. When we're solving algebraic equations, the answer is always a number or set of numbers. When we're solving differential equations, the answer is an entire equation. So the question here is, what function y as a function of x could we plug into this equation to make it a true statement? Go ahead and pause the video and see if you can figure that out. Now here, and again, we're not kind of diving into the official techniques yet, but we're just kind of trying to common sense our way through it. Basically, another way of thinking about this is, what function y has a derivative that equals itself? So think about all the equations you know that have derivatives that equal themselves. There's actually only one, and that is, if you think about it, y, I won't explain how we got that. We're just kind of guessing and checking at this point, honestly. But y equals e to the x would also work. So if you plug in e to the x here, you can verify that, yeah, the derivative of e to the x is e to the x. So if I were to plug this in, you can think about it. For y, we plug in e to the x. And then for here, we plug the derivative of y, which is dy dx. Well, that's also e to the x. So yes, for any value of x, the derivative does equal itself. That's a true statement. But that's not all. There's actually a bunch of other equations that would work. So if you think about it, y equals 0 would also work. So y equals 0 also works. And again, if you don't believe me, just verify it. Plug in 0 for y. And then on this side, what's the derivative of 0? Well, also 0. So if you actually plug this solution into the equation, you get 0 equals 0, which is also a true statement. Another solution, there's a bunch of solutions, but y equals 2 e to the x would technically also work. Or y equals 3 e to the x. And again, you can verify that. If you take the derivative of 2 e to the x, it equals 2 e to the x. And then, you could have y equals negative 7 e to the x. Hopefully you can see here the pattern. There's actually an infinite number of solutions, I guess is what we're getting at. And we'll talk about how to deal with that exactly later, but just notice that, yeah, actually all of these are valid solutions. If we plug every single one of these into the equation, we would get a true statement out for any value of x, and that's the key. It has to be true for any input to the function possible. Now, just for context, if you go into a math or engineering curriculum in college, you will probably take a course called differential equations. And all you do in that course for an entire semester, basically, is just solve differential equations. As much material as like in a calculus AB course, think about like the calculus AB. If you're in AB, think about how much material is in there for the entire year. And then if you're in a BC class, take about 75% of the material in your class. That amount of material is the amount of material in the differential equations class, except all you do is solve differential equations. So differential equations are actually a pretty massive subject, even though it is easy to not understand, or it's easy not to think that after your exposure to them in like AB or BC, because you only see a small portion of them. Basically, in one of those courses, the reason there's so much material is because there's so many different types of differential equations, and I have a lot of these listed out. So like a lot of these, again, this is not everything that you would do in a course, but it's just kind of a sample. These are like the various techniques that you can use, that you learn in that course to solve different types of differential equations. And like these down here, these are like specific physics equations that are useful to describe with differential equations, and you learn how to solve those as well typically. But the point I just want to make here is that there's a massive amount, like depending on how you count, like 15 to 20 plus different types of methods that you can use to solve differential equations. Now, the good news is that in Calc AB or BC, you only have to worry about one of those techniques, and that is called separation of variables. Specifically, if you have what's called a first order differential equation and you're solving by separation of variables. We'll talk about what first order means later. But basically, the point is you only have to worry about this one. So let's go into how to do that one right now. So we're going to take the differential equation we started with earlier, dy dx equals y. We already figured out through common sense what the answer is. It's either y equals e to the x, 2e to the x, or pretty much y equals pretty much any number times e to the x would work. Now what we're going to do is find that same answer in a far more systematic way. And the good news about this way is that once you learn this technique, again, this is one of the 15 techniques that you would learn in a typical differential equations course. Once you learn this technique, you can use it to solve almost everything that you'll see at this level. Because again, at this level, basically, if they're asking you to solve a differential equation, it has to be a separable differential equation. That's the only technique that you have to learn at this level because it's an intro, essentially. So just to clarify again, this technique is called separation of variables, and the whole reason for that is because of what we're about to do. We separate variables onto different sides. So here, think about what we have. I have a dy, a dx, and a y. Basically, what I'm going to try to do is separate all of the y's onto one side and all of the x's onto the other side. So the way we would do that in this specific case, hopefully it makes sense, is that and I'll do it in a few steps, but the first step you always do with these problems is multiply both sides by dx, and that'll at least split that. Now here, I kind of consider this an abusive notation because dy dx, remember, that's not a ratio. It's a function. Like the derivative is a function, so you can't just split things. You can split ratios like algebraically, but this is like a separate function, so you can't really do this. I won't go down the rabbit hole too deep, but basically, this is what I'll say about it. It is breaking the rules to split things like this, but it's very convenient, and you get the same answer that you would have gotten if you followed all the rules, but you can do it with a lot less headache. So basically everybody does this. This is like the official method that you see in textbooks, and this is what you'll always see when they teach you how to solve differential equations with separation of variables. So, but it is, again, it is technically an abusive notation, so just adding that caveat. But anyway, if we continue past that, basically we got dx on the right, we have dy on the left, but the problem is we still have the y's or one y and a dx mixed together. So how can we get rid of that? Well, basically just divide the y onto the other side. And now we have successfully separated variables. So at this point, we've separated variables. So that's good. Once you have separated variables, then you basically just integrate both sides. And on the right side, by the way, you can think of this as 1 times dx, if you want to think of it like that. So the function we're integrating is 1. And yeah, now we can basically continue like this, integrating this and seeing what we get. So if I integrate this side, hopefully it makes sense that I get natural log of y plus c, and I'll write c1 here equals cy in a second. And then the second thing on the right, if we take the integral of that, hopefully it's clear that we get x plus, and I'll write c2. Now, in this case, this is a little bit counterintuitive. Whenever you take the integral of both sides, you're going to add up you're going to end up with an arbitrary constant. But the trick is, what you can always do here is you can always kind of subtract C1, the first constant, onto the other side, because again, that's what we're trying to do anyway. The whole point of this technique is that we're trying to get y by itself. So doesn't it make sense that if we just subtract C1 to the other side, you can now combine these constants C2 minus C1 and think about it. What is one arbitrary constant C2 minus a different arbitrary constant C1? Well, it's just a third arbitrary constant C3. But we don't know what any of the arbitrary constants are to begin with, so you can just leave it as C. So I guess what I'm getting at is when you're solving these, like logically, every time you do the indefinite integral, you need an arbitrary constant. But in practice, because you can always subtract it and move it to the other side and combine them, you can basically just do it on the right. And that's what you'll typically see. So here, if I have natural log of y equals x plus c, this is what we would typically write. And you could just kind of skip this step as long as you're aware of that. So that's good. And then now remember, the goal here is that we're trying to solve for y. So how would we do that? One thing we can do, well, actually think about it like this. Why is y not currently by itself? It's because we're taking the natural log. So doesn't it make sense that in order to get y by itself, we need to effectively undo the natural log? How can we do that? What's the inverse of the natural log? The exponent. So if we specifically e to the x. So if we do what's called exponentiating both sides, and again, this is important, you have to do it to the entirety of both sides. One kind of mistake that a lot of students will do is they'll leave the plus c on the outside, but you can't do that actually. The plus c part has to go on the inside. And if we do this, hopefully it makes sense that we end up with y, because e and natural log cancel out, and then we get what? E to the x plus c. So there you go. That's the answer. Now, even though this is the answer, we can still simplify it a little bit more. So for example, think about this exponent property. If I have something x to the power a times x to the power b, there's an exponent property that says that whole thing you can instead think of as x to the power a plus b. Basically, if you have two things multiplied together and they have the same base but a different exponent, then you can basically just add the two exponents together. Again, I won't go into why that's true, but it is a valid exponent property. So here, hopefully it makes sense that you can look at x as a, and you can look at c as b, and you can look at kind of x here as e. So hopefully it's clear that we can rewrite this thing as y equals e to the x times e to the z. And now the next question is, what is e raised to some arbitrary constant that we don't know? Well, it's yet another constant that we don't know. So this whole thing basically becomes c. So you have e to the x times some arbitrary constant, which is how we get to the very end where we say y is equal to c times e to the x. And if you recall from above, that was our answer. Effectively, what we found is that logically, it would be a solution to the differential equation if it was y equals some number times e to the x. And that's effectively what we have here. C could be any number. It could be 1, negative a million, pi, or it could be 0. That's why y equals 0 was a solution before. So there's technically an infinite number of solutions, but they all have the same general shape, and that's given by this. This solution, y equals c times e to the x, is what we call the general solution. In other words, there are an infinite number of solutions, but they all have the same general shape and the same kind of behavior in some way. And that's what this formula is representing. So technically, no matter what c is, it would look, except when c equals 0, everything else would look like an exponential basically. And that is what would solve this differential equation. Now, sometimes what they will also ask you to do, actually often is what they will also ask you to do is to find what's called the particular solution. And the only way you can do that is that if you have the general solution, they need to give you what's called an initial condition. And again, I find the name initial condition a little misleading. It doesn't have, like when I hear initial condition, I think that the input has to be 0. That's actually not true. It just has to be any point on the curve. So when they say initial condition, they basically mean they have to give you some point on the curve, y, of the solution. So here, let's pretend that they gave us this point. So it's essentially what they're telling us is find the function y that one, satisfies this differential equation, and two, goes through this point on the curve. Think about what value would do that. Basically, the way you can find that is you can take the general solution. So I'll take the general solution down here. And effectively what you do is for y, we're going to feed in 3. And for x, we're going to feed in 0. And then after you do that, after you plug those two in, you can effectively solve for c. So think about what this would become over here. So this would become 3 equals c times, what's e to the 0? 1. C times 1 is just c. So basically we just figured out that c is equal to 3. So the particular solution in this case, and again, it's only, this is the particular solution because they gave us an initial condition. If they gave us a different point or a different initial condition, we would have a different particular solution, even though we would have the same general solution. So here, in this case, this would be the particular solution. So this is what differential equations are all about. But before you go, I want to give you another way to understand them, and that is called slope fields. Now, what exactly is a slope field? It is basically a field of slope. That probably doesn't help. So what does that mean? Basically what it means is that at every single point in the xy plane, you can take that point and you can figure out the slope at that point, and you can essentially draw a little slope. Now, why is that useful to us? Let's look into it. So here, let's pick, for example, 1, 0. So x equals 1, y equals 0. And then we can ask ourselves, what would be the derivative at that point? Basically, all we have to do is plug in the coordinates x equals 0, or x equals 1, and y equals 0 into our differential equation, and it will tell us the slope. Now, in this case, this only depends on y, because there is no x in the differential equation, but normally it would depend on x and y. But here it only depends on y. So if we just plug in this case, y equals 0, what do we get? We get dy dx equals 0. But what is dy dx? Remember, dy dx is still the derivative, so it's still the slope of the tangent line at each point, which means that we can draw a little tiny slope here of 0. And hopefully it makes sense that for this equation in particular, that would actually be true of all of these values. Because it doesn't really matter, like in this case, in this specific case, it doesn't matter what x is. Normally it does, but here it doesn't because we just have y. And you can do kind of a similar thing for each of these. What would this coordinate be? 1, 1. So if I plug in x equals 1 and y equals 1 to here, I get dy dx equals 1. So I should draw a little slope of 1. And again, that would be true of all of these. And then if I plug in this point, 2, 2, hopefully it makes sense, I get a slope of 2 by the same logic. So you can literally kind of, at each point on the curve, you can draw a slope. And then for this, these would be -1. And then those would be -2. So just for like that, that's what the slope field roughly would look like here. And again, you can do this for literally every single point in the xy plane, including like so right here, for example, it might look something like that, slightly above 0. Here it might look like 1/2. And you could literally find out the exact values of the slope at each point. And then that can give you an idea of if that point is actually on the solution, what would the slope look like there? So that's effectively what we're doing. One other reason I should mention for why this is so useful is that this technique, slope fields, this works to approximate the solution to a differential equation, even if you cannot solve this differential equation. Because just to be honest, not all differential equations are separable. Remember, there's many other techniques, and there are many other differential equations that you can't solve with any technique, actually, or nobody has ever figured out how to solve it by hand. You can always number crunch with a computer to estimate, but we're talking about getting the exact solution by hand. And at this level, in a Calc AB or BC course, the only technique that you learn is separation of variables. So if you have a differential equation that is not separable, that cannot be solved with that one technique, you actually just don't know how to solve it. In those cases, you can still use slope fields, though, to get a pretty good idea visually of what the solution is going to look like. So hopefully that makes sense. So now let's take a look at the full slope field for this differential equation. You can use this animation. This is just a Desmos animation. You can grab the link in the description, and I highly recommend that you use it on your actual homework problems because it will automatically create the slope field for you. Basically, all you have to do is, if you can get the differential equation in the form dy dx equals something, you basically just plug that something in here, and then it will automatically graph the entire slope field for you. And it also has this movable point right here, because remember, the slope field is really at an infinite number of points. We just don't show an infinite number of points because then we wouldn't see any white space and it would be impossible to see what's going on. So we only draw it usually at a certain sample of points. But you can take this movable point and move it around to figure out what the slope is everywhere. So I highly recommend using this. And now we're actually going to use it for this problem. So like I said, even if you don't know how to solve a differential equation, or if you just can't solve it with known techniques, you can still use slope fields to get a pretty good idea of the shape of the solution. So here, right now, we already figured out that the general solution is y equals c times e to the x for some constant c. If I turn that on, you can see that this exponential equation, hopefully you can tell that it is going with the slope field at every single value. And again, according to the general solution, we will have an infinite number of different values, but no matter what c value I change it to, it's always going with the slope field. Even if it's at y equals 0, you can see that whenever y is equal to 0, all the slopes are also equal to 0. So even this is still true, I guess, at c equals 0. So if we bump this up, but in general, this is how you can think about the solution curve at every point. Now think about what it would look like for a curve that is not the solution. So right now you can see I'm just turning on y equals x squared here. It definitely looks to the right. It kind of looks like it's going with the slope field rather than against it. However, if you come over here, like right here, for example, this is a good example, you can see that the slope in the slope field is completely perpendicular to the actual tangent line or the slope of the solution curve there. That's how you know that this one, like y equals x squared, is not actually the solution to the differential equation because it's going against the slope field. It's actually going against the slope field in many spots, but it only needs to go against the slope field in one spot. If it really is a solution, like we have for y equals c times e to the x here, no matter what c value you change it to, it will always go perfectly with the slope field at each point. So like if I take this movable point, you can see that if I come down here, I'm just going to try to move it along the curve, even though it won't be perfect. You can see that no matter where I go along the curve, it's always going exactly with the slope field. So that is how we know that this truly is a solution to the differential equation. So that's the general solution. Now the question is, what about the particular solution? So remember, with the particular solution, you need a single point on the curve. So that's this 0, 3 that you can see right here. And I'm actually going to turn off the slope so that it's easier to see. So we already figured out the general solution to the differential equation. It's this curve, but hopefully it makes sense that even though there's an infinite number of c values that would satisfy the general solution, there's only one c value that satisfies the differential equation and makes it go through that single point. And you can see that that is 3. If I go past that or below that, it will not go through that point. C has to be exactly 3 for it to go through the initial condition or the point that they want. And that's why that's why y equals 3 times e to the x is the particular solution in our case. So there you go. That's an introduction to the theory behind differential equations and slope fields. I hope it all makes sense. If you want to grab the slope field animation, which I highly recommend for your own homework problems, be sure to check the link in the description. Otherwise, I'll catch you next time. See you.